Okay, and for the sake of the recording, just mention again, this is one of our digital events. Thanks for joining today. So I'm Christy Callback-Rose. I'm joining from California. Thanks to all of you for joining from wherever you might find yourself today. And we have a couple of talks. First one will be GPUDirect Storage with Spectrum Scale. And the second one will be Spectrum Scale performance improvements. I want to thank our speakers. So first up, we'll have Kiran Modukuri and Ingo Mintz. Kiran is joining us from NVIDIA, where he's an engineer on the DGX platform software team and has been focusing on I/O pipelines, especially around AI and machine learning. Ingo is joining us from IBM and has been working with Spectrum Scale for more than 10 years. He's currently focusing on RDMA and other things related to GPUDirect Storage and AI workloads. I'd also like to thank Ulf Troppens and Kedar Karmarkar for arranging all the things around the event today. And we do have a Q&A option available. So if you would use that as the speakers are talking, you can enter your questions and we'll try to answer those along the way or jump to them at pause points. Okay, next slide, please. Okay, I'm not going to read that one for you. You can read that yourself. Disclaimer about what is mentioned here versus the reality of plans in the future. Okay, next slide, please. Okay, and with that, looks like we're ready to begin the main content. So let's welcome our speakers, Kiran and Ingo, and I'll turn it over to you. Thank you.
This is Kiran Modukuri from NVIDIA. Today we'll be presenting the overview of GPUDirect Storage, the use cases, and some of the internal benchmarks. And Ingo from IBM will be presenting more details on how GPUDirect Storage has been leveraged with Spectrum Scale, and he'll be presenting more data on that. So with that, let me get started. So GPUDirect Storage is one of the Magnum IO technologies that leverages basically the DMA and RDMA engines available in the NIC and the NVMe hardware to drive data directly from storage to GPU memory. This has many advantages, especially with higher peak bandwidth, lower latency, and reduced CPU load. As you can see here, the data moves directly from local storage directly into the GPU memory rather than going to the CPU root complex, going into the system memory and back into the GPU. It involves multiple bounce buffers as well in the software, and GPUDirect Storage, as we'll see, will avoid all those bounce buffers and try to go directly from the local storage or from the RDMA NIC directly into the GPU memory. So this is a very high level, the software architecture for the GPUDirect Storage. It involves a set of user space libraries. We call them libcufile or cufile APIs, and a kernel driver accompanying that to orchestrate all the DMA bar memory mapping and interfacing with the virtual file system. And the way we have done this is basically changing minimal things in the file system driver, the block IO system. And there's plugin architecture where the implementers of the file system with GDS have to implement certain set of callback functions where the DMA translation is happening. And as we'll see more detail in the next few slides, this basically allows us to work with many vendors and provide a direct path from storage into the user space applications. And these cufile APIs that we present here are very similar to POSIX-based APIs, but this is something that we have developed as part of the GPUDirect Storage. This slide shows a simple example. More details are available in our web link that's shared here. But at a high level, the application developer or the data loader in a PyTorch or TensorFlow API framework would do something like this. They would open the driver open, which allows the library to communicate with the driver. Then you open a regular Unix file descriptor. You register that with our API so that we can track whether this particular file is GDS enabled, what is the routing that is required for this file descriptor. If it is an RDMA based file system, then which NIC to use. All that decisions are happening as part of this registration. Then the next stage is to do something called CoFile buff register, which is basically a CUDA malloc memory is registered. And at this point, we open up the bar space, try to keep the metadata ready for any DMA that's happening in the next set of IO calls. The second set of calls is the IO calls, which basically do the CoFile read or write. And they, as you can see, they're very similar to the POSIX read and write APIs with absolute offsets, size, and the device pointer offsets. So once this call completes, the data is in the GPU memory, and the user can do any new CUDA kernel launches or anything that they want to do within in the GPU memory. And you can see there is not any other malloc buffers or anything present in this. The last stage after you have done multiple reads and writes is to deregister the buffer. So you're freeing up the bar1 memory space. And you also deregister the handles so that you can close the file descriptor and you can release the memory. The last stage in the application is to close the drivers. So any registration that are done with the vendor partner drivers are all released. And even the driver can be unloaded at this point in time. Moving on to the next slide. So this one shows a simple chart based on our DGX2 synthetic benchmarks called GDS-IO. As you can see, we have done testing with the traditional way, which is to bounce through the CPU bounce buffer into the GPU memory, or through the same data read through the page cache, with part of it being not populated. So you have to populate the page cache, followed by getting into the user memory, and then copying back into the GPU memory. And as GDS, you can see that once you start at 32 KB or so, you start seeing the saturation because of the drives that are there. So we had, in this case, the maximum was 54 gigabytes per second with the DGX2 platform. And you can see that we saturate very cleanly on the throughput side. And the latency profile, as you can see, there's a lot of jitter in the other workflows because of the CPU being involved. And with GDS, the latency remains very stable there. And the next chart is just showing the depiction that basically the amount of CPU used in GPUDirect Storage is reduced. As a result, you can see the throughput and the latency improvement. This is going more detailed into the mechanics of our CoFile library. As I said before, it's a user space file IO library for GDS data traffic. It can perform DMA and RDMA traffic from different file systems. And similar to pread and prewrite, we can support direct IO for aligned IO. In addition to that, we can also wrap all the unaligned file IO offsets and sizes so that the user does not need to do something different for unaligned IO. And one of the main purpose of this library is to avoid CUDA copy, the intermediate copies to page cache, and perform a direct transfer from the storage into the GPU memory. In addition to these features, we have something called dynamic routing, which basically tries to figure out the hardware topology during the driver open, tries to figure out what is the optimal routing based on the GPU location and the NIC that is available for the traffic, and tries to route it through our NVLink or through our PCI and NIC switches so that we can get an optimal route from the storage to the GPU memory. The last path is for the cases where the GDS is not supported for a particular file system or for a particular platform, we end up moving the data through something called compatibility mode, which is nothing but using this traditional POSIX mode in an optimal way to the GPU memory. And this is something that I'll talk in the next slide as well. One of the requirements for GDS to work is all the files need to be opened in ODirect semantics so that we are not using the page cache. And for RDMA-based systems, we need dynamically connected transport support with IB verbs. This is present in the Mellanox adapters, and this is something that we use for GPFS, our Spectrum Scale. This is more talking about the kernel drivers responsibility, why we need one. So most of the current implementations in the Linux implementation, we don't have a direct access to the GPU memory. This is a memory that's exposed behind the PCIe device. So there is no direct support for struct pages. So what we do is wrap these struct pages using system memory, and then there is an indirection internally for passing through the different file system layers. So this particular driver provides exposing the DMA bar1 space memory, providing struct pages or proxy pages for the GPU memory down to the file systems, and providing a callback interface so that during the DMA translation, we can detect that this is a GPU memory and translate from a virtual address to a DMA bar1 address. In addition to that, for GPFS, we have added support to basically share the remote keys, the LID, GID information for a particular memory registration with the GPFS daemon. And this particular drive is also available on the GitHub at NVIDIA GDS, NVIDIA FS, if you want to take a look at this. And this is a GPL-v2 licensed module. I have covered this briefly before, but dynamic routing is basically the feature that we have in our library to detect the hardware topology between the storage and the GPU. And for local storage, we can leverage the NVLinks to transfer the data or NVLinks instead of PCIe switches. The other thing is for GPFS, we can, based on the available set of interfaces, we can detect the optimal interface that we would like to have the data come on. And this is something that is done in the library. In addition to that, we have different decision making around whether to use compact mode, which is to use the POSIX mode in case the file system does not support, or if the offset or the buffer alignments are not optimal for GPUDirect storage. And all this results in reduced latency and increased throughput. So a little bit more on the compatible mode. This basically, what we have seen is like there's a slight overhead at the lower IO sizes because of the bookkeeping that we do to track whether this particular file supports GDS or not, or whether this particular IO has a different alignment requirements and copying the data. So compared to the POSIX, we have slight degradation in the lower IO sizes, but at a higher IO sizes beyond 32 KB and 64 KB, we are almost the same as the regular traditional way. So there should not be any degradation using our APIs for file systems that don't support GDS all the way through. And this is the detailed architecture. Let's spend a little bit more time on this one. What we have is basically two workflows. One is the allocation of memory. So traditionally, we allocate the memory, then we register the buffer. And once we do that, we get a VA to PA physical address mapping. And for GPFS, the additional step that we do is to expose this memory to the RDMA NIC. So we call IBverbs API with our Mellanox PA-Direct technology to expose this memory and program the NIC with the information and get an R key, L key, and basically the LID, GID information. And this is basically cached in our library during the buffer registration. And during the IO, we send this information down through the NVIDIA FS.ko kernel, goes to the VFS, reaches to the Spectrum Scale, MMFS Linux driver, and then there is a callback that happens from the driver into the kernel module asking for a VA to physical address translation. In that, it also asks for all the information about the RDMA information, which is the R key, the LID, GID information, which is used by the GPFS daemon to pass it to the remote server. And the remote server can now do an RDMA write or a read directly from this exposed memory. So as you know, with the RDMA write and read, the client becomes a passive entity, and only the control connection is the one that's actively asking, requesting for data or trying to write the data. Moving on to the next slide. So this is talking about more of the hardware and software support that we have with GPUDirect Storage. Today, it's all x86 64 based, no other platform is supported. We support ConnectX-5 and ConnectX-6 NICs to get the DC transport support. And we support on all our flagship products like the DGX and other EGX platforms and HGX platforms. We support all the data center GPUs starting from Volta and to the latest Ampere-based systems. And for GPFS, we require MoFed 5.1 and above. We support all the Linux kernels above 4.15, and we support all the standard Linux distros like Ubuntu 18.04, 20.04, and Red Hat Linux starting from 8.4. And for platforms and distros where we don't support, we support compact mode in RHEL 7.0, in the Debian 10, CentOS 8.3, and so forth. In addition to this, we have some of the restrictions when you're using GDS. This is currently supported for Linux only. There is no Windows support yet. And we are not supporting virtual machines or VM environments yet. And we require that all the files be opened in ODirect mode. And this basically does not support compression, checksum, inlining, as they all need buffering to the page cache. And we are not yet supporting anything beyond the Mellanox adapter. So we'll require basically ConnectX-5 or ConnectX-6 NICs to support the DC transport. And the IOMMU transport, basically, the support is limited to DGX platforms. We have not tested with all IOMMU, and some of the IOMMU we have seen issues. So we recommend disabling IOMMU support and ACS for performance. And these are the few restrictions with the current GDS design.
So before you move on, looks like we've got one question about Power9 support in future.
Sure. I mean, I have Sandeep as well on the call. So from a release point of view, I think we have not yet planned, but that is something GPUDirect Technologies is known to work on Power9. So there's no technical limitation. It's mostly around like the support and the requirements coming from, I think, the customers and partners.
Just to add to what Kiran said, it depends on the demand and interest.
Okay. Moving on to the, so these are additional set of restrictions with the current IBM Spectrum Scale. And all these are supported in compact mode. So the end user does not see any failure for these use cases, but the GDS mode will be turned off dynamically during the IO point whenever this sees for writes. All writes go through the compact mode. And we don't support any of the encrypted memory map files, compressed files. And some of the restrictions are already listed on the Spectrum Scale website, so you can look at that more detailed. We just wanted to bring up that there are cases where GDS is not optimized for Spectrum Scale, and you want to be aware of that. So quickly going into the various ecosystem that we have worked with over the last 2 years with various frameworks, readers, and other partners. So we have integrated to a different set of frameworks in the visualization. This is basically 3D volumetric data visualization for simulation data, something like the Mars lander, or for any of the volumetric data in, visualization that with NanoVDB and OpenVDB, if you have seen that. So Index is our NVIDIA product that basically can do 3D volumetric visualization. And GDS is a plugin to load certain data formats which Index uses. And we'll be talking in the next slide more on this one. In the healthcare side, CoSIM is another data library that works on top of Rapids. And this is used for n-dimensional chunked images and stuff for medical use cases like the X-ray and MRI scans. The next set of area vertical that we have integrated is data analytics. And Rapids is our framework for integrating with GDS, where we can have something called CoDF format, which is a columnar database in GPUs that we can basically leverage the parallelism. And on top of Rapids is cuSIM, Spark, and NVTabular. All this are still in works, but these are basically leveraging the core functionality of GDS. And we have some more work in the molecular modeling in HPC environment from other universities. And there is an integration to PyTorch, TensorFlow, and MXNet via our DALI plugin, which is our data loader for images and video. And there are additional work we have done with databases outside called HeteroDB. It is for PostgreSQL that has seen advantages. And for coming to the benchmarking tools, we heavily use GDS.io, which is an in-house developed tool to compare between different modes of I/O. And GDS has been integrated with the current FIO and another benchmark called LBencho. So you can look into benchmarking the standard tools as well. And in addition to the frameworks, we have many of the readers in open source as well as in works. Like HDFI is one of the popular data format that has been integrated with GDS. And there are variations of it with parallel HDFI and serial HDFI layers that has been integrated. And some of the work is going on with MPIO and OpenMPIO at University of Houston and Aragon National Laboratory. So this is all still in works. And there is some more additional work on ZAR, which is an n-dimensional chunked array format for Python and NumPy. That's also in works. So you'll probably see in the coming year more integration with the frameworks and getting more into production side of things. So very quickly, let's go through the use cases for where we have done with the local storage. So this is not saying that this is the only benchmarks we have done. We have done with other partners, but for this discussion, I think I would share the internal benchmarks that we have done with the local drives. And this is for the volumetric video processing that was shared in Jensen Huang's keynote demo in the SC21. This is for Verizon's volumetric video processing. They have their own proprietary video processing pipeline where they can take the data over current storage, read and write the data. And with GDS and NFS or RDMA, they were able to achieve the full line rate that they're expecting, and they can scale linearly with their a number of NICs that they have in their processing system. So this is a case where the data is streamed heavily into the system, and we would like to see GDS benefits here. This is the visualization using the NVIndex and NanoVDB data format on our local NVMe storages. So with this, we were able to achieve 10 frames per second for a real-time data visualization. And we were able to max out the entire 47 gigabytes IO bandwidth. And this is a purely read traffic. This is something that requires a lot of data processing, and it's directly bound. The frame rate is bound to the data that you can be streamed from the storage. And you can see this on the YouTube as well as in any of the SC19 talks, SC21 talks. And this is just showing a demonstration of our DALI plugin with GDS and PyTorch. So we were able to gain some decent benefit with even local NVMe storage with around 1.17x gain. And on the inference, I don't have the data today, but there is much more higher because of the data being the bottleneck there. And finally, I have another HPC benchmark in oil and natural gas exploration. This is called reverse time migration algorithm, which basically has the data for seismic data analysis. And there's two different kinds of modeling, forward and backward modeling. And these all require heavy parallel data reads from the collected data. And we could see improvement even with the compression that is present in the data. And they use something called NVComp, which is another library within NVIDIA to basically load compressed data directly from storage into the GPU memory and then decompress and basically run their reverse time migration algorithm. And we have seen decent improvements there as well. So one key takeaway is basically around anytime you have data as a bottleneck, you can process the data in GPU. GDS is something that will definitely help there. So with that, I'll move on to sharing the Ingo. Ingo, if you want to present it directly.
Yeah. How can I can you stop sharing?
Yeah, thanks.
Thanks very much for your talk, Kieran. If you have any other questions for Kieran, please drop them in the Q&A, and we'll begin with Ingo's presentation here in a sec.
Okay, so slides should be visible.
Looks good.
Okay, good. Thank you. Yeah, so thanks, Kieran, for the introduction, or actually for the deep insight into GDS. So now from the IBM perspective, what have we done to actually make this fly so that our customers can use it? And so some of you may know the tech preview in 5.1.1. So I joined the team when basically we started with the G8 version for 5.1.2, so which is now half a year ago, approximately. And so let's see how far we got. So some disclaimers. I think we can skip that for the time being. Yes, so I'd like to explain how this all applies to GPFS. What hardware and software you need to make it work. So briefly go over the Q file read. So because that's a crucial part and the crucial interface, how you can use it. We'll show some performance numbers and then go to the outlook, what is about to come. So yeah, first the motivational slides, and Kieran has already shown a large number of applications. So here just two things to mention. So basically all applications in HPC and AI where you need to move a lot of data, where you have a lot of data, for example, grid-based data for weather forecasts like temperatures, air pressures, wind speeds, and stuff like that, where you need to put them quickly into your GPU in this case, so that you can actually leverage short latencies and high throughput. Or Kieran also mentioned the reservoir and the seismic applications where you also have grid-based data for the different densities and the layers within the earth to find where your oil and gas actually resides. So that means basically this is all about short latencies and high throughput so that your applications can move much quicker than before. So how did we do this for GPFS? So typically, for those of you who are familiar with GPFS, GPFS as a clustered file system comes client-server fashion. So the classical model is you have an NSD server. That means basically you can have local disks, or you can have, for example, fiber channel LANs, which get served by a so-called network shared disk server, so the NSD server. And there's a cache on the server side. And typically, if the client likes to read some data, the data is first fetched from the disk into the server-side cache, the page pool. Then, of course, it's moving through the fabric, InfiniBand in this case, into the client-side page pool, so the client-side cache. There, it can be copied into the application buffer. And finally, if moving this path, the data has to be copied into the GPU buffer. So that means there are 4 steps. And now with GDS, basically it's reduced to 2 steps. So in the fashion of a DMA, of a direct memory access, and in this case an RDMA, because it's remotely between the client and the server, The data is first fetched from the disk into the page pool, and then copied through the InfiniBand fabric directly into the GPU buffer. And Kieran has shown the picture how the actually CUDA libraries interact with the kernel modules and the GPFS modules, so that basically the RDMA that is started on the server side is able to know the right memory buffers where to move the data, so that we get the client side cache out of the way, and we also get the application buffer out of the way. And so we can increase the throughput and we can reduce the latencies. And furthermore, the CPU on the client side is not involved in this RDMA, so that basically you also save CPU cycles your application can use for other things. So this is currently the only model that is implemented in Spectrum Scale. So you need an NSD server, you have a client, and the NSD server can be, for example, an ESS, so an elastic storage server out of IBM storage portfolio, or it can be a classic NSD server serving fiber channel LANs or whatever. So, but you need the NSD server on the server side. Okay, so from a software side, what do we need? We've tried to document all around GDS, that means the different version numbers and version levels, in the FAQ, which is a large document, but you get a section there on GDS, and it will tell you the current supported configurations. So from a hardware perspective, we are running on x86 with a GPU supporting GDS. So it's, I think the smallest model is the Tesla T4, and it goes up to the A100. And Kira mentioned basically currently today, all of the data center GPUs are supported. Then you need a storage server, and this is just what GPFS supports. It can be anything. This can also be Power. I've seen a question in the chat, on the Q&A chat, about Power9. Yes, on the server side, we are supporting this currently, either a classic NSD server or an ESS. You need the InfiniBand fabric. So we are using CX4, 5, and 6. I think the official support statement for the NICs is that the CX4 is not supported by officially by NVIDIA. It works for InfiniBand, but that will change if we take a look at Rocky in the future. Yes, and so as I said earlier, we are starting to GA this functionality with 5.12. This was last year, and so we will see what the next releases bring. So there's active development work going on. You need the OFET stack. In this case, you need the Mellanox OFET stack because of the dynamic queue pairs which are being used, which I think have not gone completely into the vanilla OFET stack yet. So we are requiring here the MOFET version. And finally, you need CUDA, CUDA 11.4 or later. As mentioned, if we run into issues with certain level combinations, we will document that on our FAQ side. And yeah, then of course you need a CUDA C++ program with the high-level workflow that Kieran also presented already. And alternatively, you could also use a library which is already encapsulating the data transfer for you, like DALI, the data access or the data loading library by NVIDIA. Yes, so this is what Kieran already has shown, as it's the crucial bit how your applications can access an interface with GDS. I'd like to go briefly over that again. So you open the driver. You need a POSIX file handle, which is opened with DirectIO. And this file handle gets registered with the Q file handle register function. And basically, you're doing the Q file read. So that's the API that is actually getting the data into the GPU buffer. And of course, you add here the file handle, which has been registered, and the addresses and the sizes of the memory region you like to fetch from the file. And finally, you can clean up everything so that your application can close cleanly. All right, so in the following, I will show a couple of benchmark results, and so that we can understand that I'd like to briefly go over the DGX A100 architecture. So this is basically a server put together by NVIDIA, which has 8 GPUs, A100 GPUs in this case, and which has a couple of network interfaces. And this is where the interesting thing starts. So we have 2 storage NICs. I think one is already populated, one is optional. For our purposes, measurements, we have been using 2 storage NICs. And those storage NICs are connected to the CPUs. Whereas you also have the compute NICs, which are 8 interfaces, which are directly connected to the PCI switches, to which also the GPUs are connected. If you take a look at the back of the system, you will see the 8 or 4 slots on the left, 4 slots on the right for the compute NICs. You will have one of the storage NICs here on the left-hand side, and the other one, the optional, here horizontally placed. So typically, the intent is that data is moving through the storage NICs so that you save the other NICs for GPU to GPU communication and data movement. But of course, you can also use them for data, which is not the intent. But of course, you can generate more throughput because you have more interfaces which are closer connected to the GPUs. And I will show numbers for both of these cases. So first of all, few benchmarks numbers for the case where we are using the storage NICs. So the system setup for test here was 2 ESS 3200 with 2 HDR links both. And we have a Mellanox IB switch, and we have the 2 DGXs. As we've seen, we have 2 storage NICs, so we can connect each DGX with 2 cables to the switch, also resulting in 4 HDR links. And yeah, for these numbers here, we are using the storage NICs. So we have 2 scenarios. Scenario 1 has 2 ESS and just a single DGX. And the second scenario actually doubles the number of DGXs. And we are looking at throughput. And we're looking at 2 different ways of I/O. The first one is using direct I/O. That means your application triggers a direct I/O read, and the data is received and then used in the QDMM copy command to be moved into the GPU. So this would be the way if you do not have GPUDirect storage. So you have to fetch the data first into the client application buffer and then copy it into the GPU. And the second row shows the numbers with GPUDirect storage. That means this is the RDMA directly from the server-side page pool into the GPU buffer. So what we can see here is comparing the first row with the second row. So we are nearly doubling the throughput. And at the same time, when we go from scenario 1 to scenario 2, we are also scaling linearly in this case with the number of DGXs we are connecting via the storage NICs. The benchmark that has been run is the GDS I/O utility. So if you install your CUDA package, you find GDS I/O, and you can provide various options, of course, a file name, number of bytes, I/O sizes, and things like that. And so this has been used, and it's resulting in sort of a streaming workload for this benchmark. And these numbers have been generated with 1 megabyte I/O size. Okay, moving ahead. Gets us to latencies. So similar setup. In this case, we have one ESS 3200 and two DGXs. And we're trying various numbers of GPUs to be used. So remember we have 8 GPUs in a DGX. So in total we have 16. And so we have the chart here showing the number of GPUs being used and the latency in microseconds. And again, once for the GDS case, so the green boxes, and once for the direct I/O plus CUDA mem copy. That means the way you would do it if you do not have GDS. And we can see that the latency reduction is also about a factor of 2. That means we can move the data much faster. So finally, I want to show some numbers for an experimental config. And remember, we have seen the chart with the compute NICs. So NVIDIA likes to be pointed out that these are really not to be used for data, and that using these NICs for data access can impact other benchmarks they have done, of course. So if you use these NICs for data transfer, other things using the same NICs for GPU to GPU communication, for example, may suffer. But interestingly, for getting some throughput numbers, I think it's interesting to see how far we can get. And again, we have a setup here with ESS 3200 with 4 HDR links, and we are using all 8 HDR links on the DGX. And we are getting, we have 2 ESSs here. And we're getting about a throughput of nearly 200 gigabytes per second, which is maxing out the fabric to a degree of 95%. The benchmark basically is the same GDS I/O with a 1 megabyte I/O size. Okay, so moving ahead. So typically we get asked, what about writes? Starting with Spectrum Scale 5121, we basically support the writes in compatibility mode. So Kieran has explained that if the driver figures out that certain things cannot be done with GDS, the driver will issue a POSIX read, or in this case, a write instead. That means your applications can be written to use the QFile write API, and this will perfectly work. You will just perhaps not get the benefits of the GDS, because what is happening internally in the library is that we will revert back to a POSIX write in this case. But you still, if you're on an InfiniBand fabric, you will still get the direct I/O performance of GPFS. Because what happens internally is that first the library will copy the data with the CUDA mem copy command, and then a direct I/O is issued. That is basically moving the data from the buffer to the server side and into the file. So this is already out there. So again, we have here GES write acceleration on the slide for the planned future enhancements. So of course, we know that if you want to get quicker writes, using the RDMA to write the data into the file might be useful and desirable. So we are looking at that, and this may come at some point in time. As well as the support for Rocky. So we have been asked to do the same thing also for Rocky. And so we're looking at that. Basically, it's all about performance. So HDR is also moving ahead. So next will be NDR. So we are trying to see what NDR will bring, and that we will scale with the increased bandwidths being offered as well. And finally, we have identified a couple of things that we can do better. So NUMA related and other stuff, so that we will also see performance improvements over time. Yes, there's some documentation out. So as I said, GPUDirect in Scale was G8 was 5.12 last year. So you can go out there and check the documentation. So there are documentation websites for IBM, and also these things are included in NVIDIA's documentation. So you will hopefully find pointers both ways to get the full picture. Yes, and that's the end of my part of the session. I'd like to mention a couple of people here which have been contributed greatly to this work. So Felipe, John, Ralph, Sven, Willard, and Mary, and of course there are others. Yes, and with that, I'd like to thank you for your attention.
Okay, thanks very much to both Karen and Ingo for some interesting talks this morning. Do we have any final questions? Okay, so these recordings will be made available later if you need to share them with your colleagues. And thanks again to our speakers, and thank you for asking questions during the session. Always keeps it interesting. Thank you both.